So we're back, everyone, to continue to another topic in series circuits. This one is called Kirchhoff's voltage law. Whoops, wrong page. There we go. Kirchhoff's voltage law. So this is going to play off what we just showed you in the series voltage sources in the previous video. And I just want to use a textbook definition to describe in words what Kirchhoff's voltage law is. It's really playing off two ideas. It's applying Ohm's law, okay? That doesn't change. Ohm's law never changes in DC circuits. But it's also using the idea of conservation of energy. So any energy that is produced, so any voltage that is produced, has to be used up in a circuit, in a closed path, right? So in words, and sorry, I'm going to be looking at my textbook because I don't have the definition written or memorized in my brain in a nice, eloquent way. I know what it is, but I don't know how to express it correctly, especially late at night. I know you guys are probably not watching this maybe late at night, but I am preparing it late at night. All right, so Kirchhoff's voltage law is a fundamental circuit law that states that the algebraic, I know your math teachers will love that word, so the algebraic sum of all the voltages around a closed path is zero. Or in other words, the sum, just want to make that clear, the sum of the voltage drops, i.e. the voltages across the resistors, so the sum of the voltage drops equals the total source voltage, or the sum of the series voltage sources, okay? So another way of saying it, okay, is the sum of all the voltage drops around a single closed loop or path in a circuit is equal to the total source voltage in that loop. And in an equation form, that is written as V source or V total equal to VR1 plus VR2 plus VRN, where Rn is the number of resistors. That's a little hard to see there, but that says number of resistors, all right? So it doesn't always make sense when you see it written like this or said like this, but let's look at an example of it so that we see very clearly what it is. Now, actually, before I say that, I'm gonna say it in a slightly different way now. just because I want to prove that it really doesn't matter where your sources are, what direction they're in, and as long as you label your direction, your plus and minus, your higher potential, lower potential, and you just simply follow them, you'll always have the right equation. Okay. I also want to accent a little idea here, right? So it says the sum of all the voltage drops around a single closed loop or path in a circuit. So the reality is that this law, this Kirchhoff's voltage law, which we sometimes call KVL for short. Okay, we're going to refer to it as KVL. We will not say Kirchhoff's voltage law over and over again. This idea of Kirchhoff's voltage law, the KVL equation, can be done in any kind of circuit. It is always true if you pick a single closed loop. So it doesn't matter how complex the circuit is, where it goes, whatever, if you've labeled it and you keep your directions, your plus minuses all straight in a logical way, then we can write this KVL loops all over the place, and they work. They always work. This is why it's called a law and not a theory and not an idea and not an opinion. It's a law. It's true until physics is proven wrong, which is always possible, okay, as they find out more about string theory and chaos theory and all this quantum theory. Until we prove it otherwise, Kirchhoff's voltage law is always true, all right? So another way of saying this is the sum of all voltage drops or gains is equal to 0. Okay, so that's sort of similar to the one up here, but I'm really defining it as drops and gains, which will refer to which way your plus and minus is. Okay, so to solidify that idea, let's look at an example. Let me clear this. And again, if you missed any notes or whatever, pause the video and just go back, right? So let's draw up a circuit, and I'm definitely going to put multiple sources in here now just to prove that it all works out and is all beautiful and everything works the way we expect it to work because of this fact, this truth. All right, I'm going to call this, again, I'm going to be lazy. I'm going to call them all 100 ohm resistors. For simplicity's sake, I'm going to call this one a 5 volt, and let's make this one a 5 volts as well, just for argument's sake. Okay, so before we start, we're going to label everything. So if I were to sort of say step 1, label current and all, what should I call that? Potential differences. All right. So I'm going to make a guess and say my current is going clockwise. It's not really a guess. I've done these so many times that I know this is true. Okay. I know my battery is plus minus like this because of the actual battery. This one is plus minus like this. This one's plus minus like that. Because of the current flow, I know that the voltage drop across this resistor, which I'll call VR1. Actually, let me put it in red like I was in yellow like I was doing before. So VR1, this is R1, this is R2, VR2, this one's VR3, R3, this is R4, so VR4, and then the plus and minus is the potential differences, higher potential, lower potential, higher potential, lower potential, higher potential, lower potential. Okay, so because this 5 volt is in the opposite way of these two, it's very easy for students to look at this and say my V total is 20 volts. It's the 10 plus the 5 plus the 5. You'd be wrong, okay? But, you know, without thinking, we can say that. We see 3 sources. We've said, oh, sources in series, voltage sources in series add up. So it's going to be 20 volts. But I know that my directions don't line up with that statement, right? So instead, if I use the concept of Kirchhoff's voltage law, what we're going to do is we're going to go through each thing and write each voltage and put a sign in front of it based on what I see as I pass through it. And so it'll make sense when I say it. So let's write the KVL equation starting at point A, and I'm going to put point A in the circuit in a second, moving clockwise until we get back to point A. All right, so I'm going to call this point A, and now we will go, and I will write it in yellow because it seems to show up better on the blue. So if I'm at point A, following the current, I see the plus sign, and this is VR1. So I'm going to write plus VR1. Continue, I see the minus sign. So I'm going to say minus 5 volts. I'm going to continue, plus VR2. Plus 5 volts. Plus VR3. Continuing, plus VR4. Continuing, minus 10 volts. We are now back at A equals 0. So that's my statement that I put at the end there in the previous page, where we just are doing voltage drops and voltage gains and basing it on the signs that we see. You can also do it logically, all right, if you prefer, okay? I'm coming here and I lose VR1. So I could put minus VR1. And I'm going to write or think in terms of drops and gains. Okay? So we're going to see in the end, the two equations are exactly alike. And it's because of this 0. So my VR1 is a loss, right? Because we go from higher potential to lower. So I lose VR1. So minus. This is minus plus, so I'm gaining 5 volts. So it's plus 5 volts. VR2, again, it's plus minus, so I'm losing VR2. So it's minus VR2. This is the tricky one because it's a power supply, or a voltage source. So we want to say it's a gain, but we're going in through the plus and coming out the minus. So this is actually the higher potential over here. This is higher and this is lower. So in fact, my electron loses 5 volts. Continue, VR3, it's a loss. This is higher potential, lower potential. So I lose the VR3. Same idea at VR4, higher potential, lower potential. So I lose VR4. And when I get to the 10 volt source, I'm starting at the negative and ending up at the positive, so I gain 10 volts. And now I'm back at A, and so equals 0. And if you look at those two equations, you see that the signs are exact opposites. And really, all it is I can take this whole equation and transfer it over to the other side by changing the sign. And so these two equations are exactly the same. I don't care how you do it. I don't care how you view it, how you want to think about it. Either way is correct, and both will give you the right result in the end, okay? The key is to remember this one. This is the tricky one. And again, in real life, would you ever see this? Not really, okay? But the fact of the matter is yes, we can have a voltage here, and it can oppose the voltage of another source in somewhere else in the circuit, okay? So Kirchhoff's voltage law helps us to kind of write out this equation to figure out our total voltage for the sources, and has to equal all the voltage drops across the resistors. Once we find our total voltage, we can find our current and then all the other in-between things that we need. All right? So I hope that was clear. I hope that was helpful. Again, if you have any questions, send them to me by email, Mayo, ask me during the next class. And once again, this is the end of this video, and we will start the next one right after this.